Thanks very much for inviting me. Found New Jersey very hospitable so far. And I've been informed that we're running a tight ship today, so I'll try to stay on time. I'm talking about boundaries of Kleinian groups. And this is very much work in progress. And I made a point of making a slide of my co-author so I wouldn't forget with Louise, Peter Hypsinski and Louisa Paoluzzi. Okay. So I think of delta hyperbolic spaces as spaces that are a lot like H3. So I think of that as a prototypical example, and I'm very biased, and I'm sure you are too. And so I'm going to have a delta hyperbolic metric space is just a geodesic metric space where the hyperbolic triangles are delta thin, and that means that the delta neighborhoods of two of the sides contain the other side, just like in H2. And it's a fun exercise for H2 to do that, and in H3 as well. Okay. So, and like hyperbolic space has H3 has a boundary that's S2, delta hyperbolic metric space has a boundary, and it's like the boundary of H3. It's an extremely useful tool. And there's a boundary, and the set of points in the boundary is identified with geodesic rays, and I say, so I'll start at a particular point. So I'll draw H2 at a particular point, and the set is the geodesic rays, and I sort of think of the boundary as the endpoints of these geodesic rays, and two geodesic rays are equivalent if their images have finite Hausdorff distance. So one is contained in the delta neighborhood of each of the other. Okay, and there's a natural topology on the boundary. And so this is called the Gromov product, so with respect to some base point, where I just take the distance from that base point to one point plus the distance to the other minus the distance between the two. So you can think if 2 points are getting really far away and they're sort of staying close together, then their Gromov product's going to be high. And so when this happens, when they stay close together for a long time, then that's a little neighborhood of a point. Okay, so it's like a natural topology that you would think of for the boundary. Okay, so so of course I've had this base point, so it doesn't depend on the choice of base point. So the different choices of x are going to yield homeomorphic boundaries, so the topology is going to be the same. And when I have a quasi-isometry between two delta hyperbolic spaces, then their boundaries where this equals means homeomorphic here. Okay, so now I'm going to talk about a group being hyperbolic. And there's my favorite definition is that if you have a group which acts geometrically, so that means by isometries, properly discontinuously, and co-compactly on a hyperbolic metric space, then we say the boundary of G is exactly the boundary of that delta hyperbolic metric space. That's our definition of the boundary. Okay, so you can think that a group which acts geometrically on a hyperbolic metric space, your favorite example should be a convex co-compact Kleinian group. Okay, and this is sort of our prototypical example of the situation. Okay, so H3 is delta hyperbolic, and so is any convex subset of H3, right? Because if I have 3 points, the triangle between those 3 points will be in that convex subset, and it'll be delta hyperbolic. So a group which acts geometrically on a convex subset of H3 is a hyperbolic group. So these are often known as convex co-compact Kleinian groups. Okay, and they are delta hyperbolic in the group theoretic sense. Okay, so here I just said that. And the boundary of the group is exactly its limit set, the traditional limit set in Kleinian groups limit sets. Okay. Okay, so what if we just have a hyperbolic group in that definition, meaning that the group is hyperbolic, it acts geometrically on some delta hyperbolic metric space, and we know its boundary, and we know it has a boundary which is exactly the limit set of a convex co-compact Kleinian group. Can I say that this is, so I keep saying these are prototypical examples. Are they really these examples? Is that what's going on? Okay. So this is a source of many important conjectures. I'm going to talk about a more specialized situation, but let me just go over some of the main conjectures and results. So it's a big result due to Tukia Gabay and Kassan Jungries, that if I have a word hyperbolic group and its boundary is S1, one of our favorite boundaries, that happens exactly when G is virtually Fuchsian. So it acts on H2. All right, so S2 is Cannon's conjecture. If G is a hyperbolic group and the boundary is S2, then it acts geometrically on H3. That's still open. Okay, another favorite boundary is the Serpinski carpet. So this is going to be the limit set if I have a hyperbolic manifold with totally geodesic boundary and no parabolics. Its limit set is always going to be homeomorphic to the Serpinski carpet. So Kapovich and Kleiner have conjectured that if G is a hyperbolic group and the boundary is a Serpinski carpet, is meaning homeomorphic, then G acts geometrically on a convex subset of H3 with non-empty boundary consisting of geodesic planes. Okay, so it's exactly what you hope. This is a conjecture still. Okay, so what else? So a lot of people think and have proven that you can see things from the boundary. Let's see what other kind of things we can see from the boundary of the group. Okay, so I'm going to work not on these conjectures, but on a slightly different situation. So there's lots of other boundaries. So there's lots of limit sets, lots of co-convex Kleinian groups that have essential annuli in them, and so they will not admit hyperbolic structures with totally geodesic boundary. And here's a couple of examples of things that you can get just by playing around with Lim by Kurt McMullen. And so let's look at a particular manifold that really has a lot of annuli in it. It has the class of manifolds I'm going to talk about first has sort of the most amount of annuli as possible. So this manifold is very related to surfaces. So this is actually a Kleinian manifold. This is an embedding into into E3. So this is actually, deformation retracts to this thing. Okay, so I take three one-hole tori, and I'm going to glue them together along their common boundary component. So here, let's see if I can see how. So here's one. So this is an embedding into E3 of this picture. So here's, let me just show you. So when I thicken this up, I'm going to get three surfaces times a little interval, and they're going to be glued to a solid tori around. So that characteristic manifold of this manifold is the whole manifold, and it's going to consist of these three pieces that are surface bundles over surfaces times I, and then a solid tori. And here's one of these surfaces times I. Here's a one-hole torus, see right in here. And then this is times I is this whole right side of the picture. So here's a one-hole torus right there. That's a boundary component. Out to this boundary component, this outside is also a one-hole torus out here. And then over here, the same thing. And then there's one in the middle right here, one going from there to there. So it's just a fun way to draw it, but really you might want to think about it this way. Yeah, the solid torus binding. So this is like the core. So if you push this core in a little bit, you'll see the core there going from one to the other. So this annulus, so this one-hole torus right here is one boundary component, and it goes over to the other boundary component, and like this annulus, so there's an annulus here that goes here over to this annulus, and that's and the core of that annulus is homotopic to the core of the solid torus. Okay, so that's just a fun picture. But okay, so I want to generalize this situation. Okay, so and this so this is almost all annuli. So there's since these are surfaces times I, there's going to be all these annuli, all these essential annuli from one side to the other side of these surfaces. Okay, so we call a manifold a graph Kleinian manifold. So it's a convex co-compact Kleinian manifold that admits a decomposition along essential annuli so that each piece is either a solid torus or an I bundle over a compact surface with boundary. Okay, and I'm going to require that the boundary of these surfaces is exactly what's glued to the solid torus. I'm not going to allow any kind of funny gluing. These have been studied extensively in the literature, And so the reason that we call it a graph Kleinian manifold is exactly a Kleinian manifold with boundary. When you double over the boundary, you get a graph manifold where all the pieces are cipher fiber pieces. Okay, because when we double over these pieces, we're going to get surfaces times S1 glued together along tori. Okay. Okay. So this is one thing that you can see from the limit set boundary. You can see that you're of this type by looking at the limit set boundary. Okay, so suppose you have a hyperbolic group with boundary that's homeomorphic to the boundary of a graph Kleinian group. Then G is virtually a graph Kleinian group. Okay, so this follows really right from work of Bowditch. So let me explain this a little bit. And I think this decomposition of the boundary of the group is really important and interesting, so I just want to advertise it a little bit. So he proves, so there's a canonical splitting of the group that comes, so this is for a hyperbolic group, which comes from the topology of the boundary. So for a one-ended hyperbolic group, a local cut point in the boundary, he proves, corresponds to a splitting of the group over a two-ended subgroup. Or, of course, you could have so if I have a circle, I have a local cut point in the boundary, right? But if I have a turnover group, then I'm not going to have any annuli. So this is just that's just that case. But let's ignore the case when the boundary is a circle for right now. That'll make things easier. So he proves there's a canonical splitting of gamma as a finite graph of groups such that each edge group is two-ended. So those are going to be exactly the virtually cyclic groups. So I'm going to get this just from looking at the topology of the boundary, which in our world of Kleinian manifolds is look at the limit set. You can tell all this information from the limit set. You get a splitting of the group as a finite graph of groups along z's, or virtual z's. And the vertex groups are going to be either these two-ended subgroups, these z's, like so these annuli that you're cutting along, or a maximal hanging Fuchsian group. And I hated this. Yes, Koshin? Sarup does do very similar stuff. I'm just using Bowditch's formulation. So yeah, he does do, yeah. And other people have done JFJ decompositions for groups. Yeah, so I'm just using his notation, his statement. So it has been done in slightly different contexts by other people. That's correct. So I didn't like this terminology, hanging Fuchsian, but it's actually right because look, the Fuchsian groups are just hanging off. They're all floppy and hanging. So that's right. And then a non-elementary these groups are all quasi-convex, which I didn't say. And there's also non-elementary quasi-convex subgroups not of type 2. Okay, so that's not very useful. But these are the ones that are rigid, and these subgroups don't have any more splittings. Okay, so those are the pieces. These are going to correspond to the hyperbolic, the hyperbolic 3 manifold pieces, the real ones, the ones that have geodesic boundaries. I'll try to explain in a minute.
Does hanging Fuchsian mean like a surface with geodesic boundary?
It means a surface group, and that the edge groups are going to correspond to where the surface groups attach to the tori. So in this case, it will mean a Fuchsian group. So when I'm in a manifold case where the edge group is exactly the thing that it's hanging from. Okay.
There's no geometry embedded in the definition, like QI embedded or anything like that?
No, but they all these subgroups are quasi-convex in the group itself that I'm talking about. Okay, so let's see, how do we get this? How does this decomposition work? Okay, so M is a boundary of a one-ended hyperbolic group. And I'm going to say a local cut point, I have to draw something, is just going to look like, so it's really hard to draw these limit sets. But suppose I have like the limit set of this one, for example. Let me just try to draw the limit set of this one. So I'm trying to roughly draw the limit set of this thing right here. So on so I'm thinking of this on S2, there's this axis Z, and then there's going to be all these pieces. So I'll draw them as circles, but really they're like, these are going to be Cantor set pieces that come out here. So these are on the circle. Okay, so really these are Cantor sets. And then all along these jumps in the Cantor sets, there'll be more little things coming out of them, like this. This is a horrible picture. Okay, but this is as good as I can do for right now. And so, so the local cut points are going to be the points. So for example, here's a local cut point. if I cut it, that locally it looks like it has 2 ends. So that's what it means. And then the number of ends, that's going to be the valency of the cut points. Okay, so I'm going to classify these local cut points according to their valency. I'll give an example in a second. And then I'm going to look at the number of components that when I remove those cut points, it breaks the graph into. So like if I remove this pair of local cut points right here, it breaks my boundary into these 3 components. And what's happening, it's like removing that, that core that they're all glued together. The whole thing is going to break apart into these 3 pieces. Okay, so so I look at the cut points of valency 2. So let me talk about those first, although these are sort of easier. The cut points of valency 2, they're going to be equivalent, like these 2 are equivalent if they cut the boundary into 2 pieces. So these 2 are equivalent right here, because look, there's this piece and this whole piece. And like this one and say this one over here are not equivalent. Okay, and what happens is the cut points of valency 2 that are equivalent, just like on a circle. So if I have a circle, all the local cut points are valency 2, and they're all equivalent because any 2 points on the circle are going to cut the circle into 2 pieces. Then that gives me a virtually Fuchsian group here. Okay, so those necklaces, I'm going to get these infinite equivalence classes corresponding to this Cantor set here, and those are going to give me the hanging Fuchsian groups. Okay, so this is all what Bowditch proves in his paper. Okay, so here's a picture of a necklace. Try to do a slightly better picture here. So I look, all these are supposed to look like a necklace. If I remove these local cut points here, they're going to divide the boundary into this piece and then the rest of it, and they're all going to be equivalent. These are artifact, yeah. So this picture, like all pictures, is a lie in many ways. This says parabolics. It's not even a... But it's supposed to give you, it is a limit set, okay, and it's made using the images of these circles. So you should think of the dust here is the limit set. Okay, and I apologize. I need to get better pictures. I apologize about my lies. Okay. So then in Mn, the 2 points are going to be equivalent if they break it into 3 pieces. So like these points are equivalent, and they break it into 3 pieces, right? So that's a splitting. And then like these 2 are also equivalent because they break the whole thing into 3 pieces. They don't. But there are some along there that are equivalent by breaking into 3 pieces. Okay. And I might have a picture of that too. Okay, so I said this already. The stabilizers of M2 equivalence classes correspond to maximally hanging Fuchsian groups. And the stabilizers of the Mn equivalence classes, these ones where you break it up into more pieces, these are always going to correspond, they're always going to occur in pairs. The equivalence classes always occur in pairs, and they correspond to the virtually cyclic groups. The M2, when you have an infinite M2 class, I should have said infinite. If you have an infinite M2 class, then that's going to correspond to a hanging Fuchsian group. Okay, so, and for this infinite class, so the closure of this minus this group itself is sort of like the jump points of the Cantor set, is going to be contained in the Mn, and that's going to be how I'm going to get my gluing. So if you think about a free group acting on the convex hull of its limit set, right? Then these jumps here correspond to the boundary curves. Okay, and those are going to be in the higher equivalence class, and those will give you the gluing of the group together. Okay, and here's another example. So I try to give a better example here. So like this is a valence 3 cut point, that's a valence 3 local cut point, and they're equivalent. Here's a valence 3 local cut point, here's a valence cut point, and they're equivalent. Okay, so this will give you the graph of groups decomposition, where here's a hanging Fuchsian group, here's a hanging Fuchsian group, here's a hanging Fuchsian group, and then these are conjugates of it. Okay, so suppose I have a hyperbolic group, and its boundary is homeomorphic to the boundary of a convex co-compact Kleinian group that's graph Kleinian. So in this language that I was just talking about, this means that the vertex group in the Bowditch splittings are exactly of type 1 or 2. They're either the virtually cyclic groups or they're the hanging Fuchsian group. So you could take that as a definition. Okay, then because we're going to use the this whole graph of loop splitting comes just from the topology of the boundary, then we see that this has the exact same splitting into maximally hanging Fuchsian and virtually cyclic groups, and therefore it has the exact same graph of groups decomposition as K, because that just comes from the boundary. It's just I'm allowing myself to glue to things that aren't the boundary now. And then I'm going to glue a blue one along this curve, and then I'm going to glue another one, which I've already done in that picture, to this curve. Okay, so in that picture I've already glued the C curve along there. Okay, and so when I do my, what did I say on my next slide? Okay, so when I do my graph of groups decomposition using just by looking at the limit set, I'm going to get these graph of groups decomposition where this piece is going to be hanging Fuchsian, I can see it hanging off. This piece is going to be hanging Fuchsian, and this piece is going to be hanging Fuchsian. Okay, so I'm going to forget about those for the time being. Okay, now I want to look at this piece. Okay, so this piece is really, so to be able to make a manifold out of this, I'm going to thicken that up so that I get a one-hole torus times I. And then I'm going to glue something to the blue annulus on the top and something to the red annulus on the bottom. Now, I claim that that's hyperbolic. And the way to think about that is I'm going to look at the double of this rigid piece. Okay, so I don't want that to have any other splittings, which you could sort of believe because I sort of killed them all, but let's just think about it. So really this is going to be in a punctured torus. Oh, good question. I'm doubling across the boundary, not across the annuli.
It's like a pair.
Exactly. It's a paired manifold.
And you're doubling across the non-paired one.
That's right. So when I think I'm doubling, I'm going to suppose I thicken this all up into a complex of surfaces where it's completely thickened up, and then it'll have a proper boundary, and I'll double along that boundary. But now I just want to double along this piece to try to understand this piece. So when I double the manifold with boundary along its boundary, then there's going to be a torus decomposition, and that torus decomposition will cut off some surfaces times the S1 in the double. So I just want to forget those because I understand this.
So in this piece, the way initially the outside of the paired locus, there's two pairs of pants as the boundary.
That's right.
And you're doubling across each other.
Exactly. So if you think on the top torus, it's going to be you'll cut along that red curve, and you won't double along the red curve. And on the bottom curve, bottom copy, you won't double along the blue curve.
But you double along the two pants.
That's correct.
And what is the purpose of this doubling?
Okay, because I want to understand that this double is hyperbolic, so I want to see that this piece is hyperbolic, so it emits a structure with totally geodesic boundary.
Well, this piece is hyperbolic. It's infinite.
I'm just about to explain that. So I'm not saying this is new, but I'm just about to explain it. Okay, so here's the the purple. So this is so I'm thinking of this as a torus times S1. So sorry, this is a torus, and I'm going to make it a punctured torus. Okay, so I'm gluing the sides together. I just made it a punctured torus. Everybody okay with that? Okay. And then I'm going to cut away the red curve, say. So that's going to be like a core of this. I'm thinking of this as a torus, glue the left and right and the front and back. Okay, and then so I just cut away the red curve in the double. I did, yeah. And then let me just cut away the blue curve. And now I'm going to cut away the blue curve. You might have remembered this picture from yesterday. So this is, it's easy to see. So this action is slightly different, okay, because we've got, this is going to be a link complement in a torus cross S1, okay. But this is actually, so you can see immediately that it's commensurable to the Borromean rings, and if you look at the group, it's actually as the Borromean rings. Okay, so this is a hyperbolic. So it's known that the complement of the Borromean rings is hyperbolic. And so I'm just pointing out that that implies that this manifold with totally geodesic boundary, it emits a structure with totally geodesic boundary. So since this double is hyperbolic, the piece is hyperbolic.
Yeah, do you know who sees the result about doubling?
No, I don't know right now.
I
Such a-
see.
Oh, I'm sorry. Okay. All right. So this piece is so link complements are something that we as hyperbolic three-manifold people like to study. Hyperbolic link complements. This group is not actually hyperbolic itself. Okay. So as a group, the complement of the Borromean rings is not actually hyperbolic because it doesn't act co-compactly on hyperbolic space. However, it is relatively hyperbolic. Okay, so in some sense, its correct boundary is the S2, which I do want to talk about briefly. So we say that a group is hyperbolic relative to some set E. This should be a set of subgroups, infinite subgroups. If it emits a properly discontinuous isometric action. So notice I didn't say co-compact. Okay, so your example that you think of here should be hyperbolic link complements. That's what I think about for relatively hyperbolic. And I think that they're good prototypical examples. On some path metric space such that one X is complete and locally compact and hyperbolic. So for example, H3. And every point of the boundary is either a conical limit point. I'm not going to go into the definitions of this too much, but it's exactly what you think it is for like endpoint of a, it's a conical limit point or a bounded parabolic point. This happens for the link complement.
It's a very difficult concept, and there are various ways to look at it. So maybe you can define what exactly you mean by it.
I could, and I'm happy to do that afterwards. I actually just added this slide because I wanted people to think about it a little bit, and I really don't want to go into these details right now. That's okay. I'm happy to talk with anybody after the talk about it.
There is another talk after this.
I think there is a break. So the elements of this are going to be exactly the maximal parabolic subgroups. So for a relatively hyperbolic group, one of the best ways to think about it is it's like a hyperbolic link complement where these parabolic subgroups, it's hyperbolic relative to these parabolic subgroups. Okay. Okay, so let's try to talk about what we're doing here in the case. The simplest case, we want to deal with the simplest case where there's a rigid piece in the Bowditch decomposition. This is what we want to deal with. So we call this a mixed Kleinian surface. So it's a one-ended Kleinian group whose Bowditch decomposition, and by the Bowditch decomposition I mean exactly the decomposition that I just talked about. So it has both rigid pieces and hanging Fuchsian pieces. So, and it will also have cyclic pieces, which I'm sort of ignoring. And each such piece is a thickened surface. So every piece, even the rigid pieces, are thickened surfaces. Okay? And the boundary of each thickened surface piece is included in the set of edge groups. Okay, so here, it's included in the set of edge groups, but it's not exactly the set of edge groups here. Okay, so I'm gonna, I can't have funny boundaries hanging off. Okay. So let me just discuss this situation for a second. So what we like to say is that if you have boundary homeomorphic to the boundary of a mixed Kleinian surface group, so if you have a rigid piece but it's as simple as possible, then you are virtually of this type. Okay, we can't say that, and it might not be true, but let me just explain the situation and what we can prove. Okay, so I have a rigid surface subgroup, just as in this example, and there's two different groups, which is why I wanted to mention relatively hyperbolic. So this group here, one hold torus, this group is going to act on H3 or H2 if you're more comfortable with that, with boundary a Cantor set. And as that representation, it is a hyperbolic group. Okay, so it acts on the convex hull of its limit set. Okay, there's another very important representation of this as a Kleinian group, and that's where I think of it as a one punctured torus. So this group will also act very naturally on the hyperbolic plane with where the parabolic subgroups are actually fixed parabolic points. And so that's a very important representation for us, and that's its representation as a relatively hyperbolic group. Okay, so I might have a rigid surface subgroup. This is going to be the one where I have the associated manifold with totally geodesic boundary. So this is non-trivial here, even in this simple case, because I've got some Cantor set. And what I'm going to do is I'm going to pinch some of these. I'm going to identify these edge groups. So I'll identify the ones that give me the surface representation, but I'm also identifying some other ones. I'm identifying some other ones like this. So it's going to pinch my group. So in general, it'll look kind of more like this. Okay, so how you get from one representation to the other is you take the representation as a convex cocompact Kleinian group, so where its boundary will be a Cantor set, and then I'm going to identify pairs of points corresponding to the edge groups. But I'm going to identify the pairs of points for all those edge groups. So I have the purple one, which is sort of the traditional one, which you're used to, which is going to squeeze it so that its boundary is S1. And then I have these red and blue curves, which are going to make my boundary much more complicated. Okay, but this GV prime is going to denote that Kleinian group and the manifold with totally geodesic boundary.
So I feel like I missed the definition.
So rigid surface subgroup, so it's
the top and the bottom so that you get an asymmetrical.
that's right. So you take a surface, you have some boundary components, and then you put curves, you attach things to the top and the bottom so that it's acylindrical. That's exactly right.
So doesn't it follow from the work of Scott and Swarup, which is like a 300 pages paper in Asterix, like 8 or 10 years ago?
Okay, I'm not claiming that I'm doing anything new here. I'm just trying to explain the situation.
Okay, I'm just trying to understand what this talk is about, if there is anything new.
This talk, I'm trying to.
I traveled all the way from Ann Arbor yesterday to listen to you, ma'am.
Well, I appreciate you. I really appreciate it, and I'd love to talk to you after because it seems like you know a lot of references that I don't know about. I genuinely would. Okay. So here I have this Kleinian group of the associated manifold with totally geodesic boundary, and yes, that's exactly correct. It's a surface. I'm going to thicken it up, and then I'm going to pinch curves on the top and the bottom so that it's acylindrical. That's what I'm looking at. Okay. Okay, so here's our theorem, which is not what we wanted, and it's also in progress. So suppose I have a hyperbolic group, okay, and J is a mixed Kleinian surface group. So this is a prototypical example. We could say just let it be this particular group, which is quasi-isometric to G. So this is stronger than having the same boundary. Then G itself is virtually a mixed Kleinian surface group. Furthermore, each rigid subgroup, so when I take this representation as a Kleinian group with totally geodesic boundary, then it's commensurable to a rigid subgroup of the other one. Questions about this statement? Okay. All right, so I'm going to get all these rigid subgroups in the Bowdish decomposition. They're going to be in one-to-one correspondence because there's a homeomorphism between the boundaries. So that's going to give me a correspondence with one subgroup, the subgroups in the Bowdish decomposition with the subgroups in the Bowdish decomposition of the other one. Okay, they'll be rigid at exactly the same time because that's all determined by the topology of the boundary. And when I take this particular representation as a Kleinian group, they're going to be commensurable. Okay, so really this is a statement, and then it follows that it's virtually a mixed Kleinian subgroup. Because if I'm commensurable to a surface group, then I'm a surface group. Okay, so let me just say a little tiny bit about the proof. Okay, so GV, so I might not have introduced my notation there. So GV is going to be the stabilizer of a Cantor subset because my limit sets are homeomorphic, so the pieces of the limit sets are going to be homeomorphic. So that means that this group is going to be free. And the edge groups, so I have the edge groups, which is where this piece is glued to the other piece. I like to think of it as an actual decomposition of the limit set because it's easier for me to think about. And so that's where the limit set of the rigid piece will meet the limit sets of the virtually cyclic groups. So that's these edge groups here are going to be purple, red, and blue. Okay, so they're going to, so by Otal, so Otal says if you have a free group and you take some collections of the conjugates of collections of some words, and you identify those points, and you still get something that is planar, which we will do in this case because we know that our whole boundary is planar, so we can just identify within that boundary. Then this represents a handle body and a collection of embedded curves on that handle body, and with fundamental group, and the handle body has your fundamental group. Okay, so this is a result of autolysis. We can realize this. Oh, and I wanted to say, so this thickened up. So one reason that seems to be so difficult to see this surface here is because when I thicken this up, what I really have is a handle body, and I have two curves A. So this is a thickened up. So I'm thickening up this. So all I really have topologically is a handle body with curves A and B. So remember, these are disjoint on the handle body when I thickened it up. And then I have like A, B, see if I can do A, B, A inverse. I can do it. B inverse. Okay? So this you can be like, oh yeah, that's a surface. But this, it's not so clear. So what I really have is I have a collection of embedded curves on a handle body. Did I do that right? Anyway. I have a collection of embedded curves on the handle body, and I want to know, is there some sub-collection of this embedded curves such that those are the boundary curves of this representation of a handle body as a surface times I. Okay, so but this is really all you see topologically, and here it's difficult to see that this is a product. Okay, so by O'Toole, I have this situation. I have some handle body with a fundamental group and some collection of embedded curves on it.
What's the result of O'Toole? So the edge groups are some collection of
So suppose I have a free group. So I have, so its limit set's going to be a Cantor set. And now I'm going to form the complex where I take this, so I have some word, gamma is a collection, is a multi-word. So it's some collection of elements of my free group. And I take all the conjugates of that, and I look at their endpoints here. And I'm going to take the complex where I identify these endpoints. So this is like, in my language, is sort of like identifying the edge groups. And so some of these might be, when I identify, I might get, here. I'll just draw it like I identified them. Okay, so I'll identify all those things, and if that resulting complex is planar, then, so this resulting complex is planar, so that means that I can represent this whole situation as a handle body with some embedded curves on it that represented by those words, and the handle body has the right free group. And in our situation, that complex will be planar because our whole limit set is planar, so we could squish along there. Okay. Okay, so this, so there's these are the two limit sets of the rigid pieces, so they have what's called a quasi-Mobius structure on them. And so then this uses work of Hypsinski and Lesueur that you can get quasi-Mobius structures on the two, I didn't say what these are. These are the limit sets in the Kleinian group structure. Okay, so now Bonk, Kleiner, and Marenkov have rigidity. This is a Schottky group. This thing, the Schottky group is a complement in S2 of some round circles. So this limit set, this is a terrible picture. This limit set is the complement in S2 of some round circles. They might touch. Okay, so it's not necessarily a Serpinski carpet. In fact, it won't be. Okay, so it's called a Schottky set. And they've proved rigidity of Schottky sets. Totally great result for this situation. So that means that they're actually Mobius. Okay, so there's a Mobius transformation taking one of these Kleinian group limit sets to the other Kleinian group limit set. Okay, so that's a very helpful result for us. And so the group.
This is really not nice because that's the result of a person who's dead. Yuga, the late husband of Karen Smith, worked on it, and he worked on it with Bonk.
Okay, so I'm totally unaware of that, and I just found out about this paper like a couple of months ago. So I would very much like to know.
It was a long old result. He's dead 10 years ago.
Okay, so I would like to know about that reference, and please tell me after the talk so that I can get it straight, because I don't know about that. Okay, so, and this group is discrete, because if I have a sequence that's getting closer and closer to the identity, then it'll eventually fix 3 of these balls, and they'll have fixed points in it. So there'll be 3 fixed points that are fixed, so it'll be the identity. Okay, so that gives us the commensurability, which gives us, if you're quasi-isometric to one of these very simple pieces, then you are actually of that type, and then your pieces are commensurable. Okay, it's almost definitely not true. I could bet $100, millions of, well, not millions, a lot of dollars, that you can be quasi-isometric to a mixed Kleinian surface group, and the whole groups aren't commensurable. I'm just completely convinced of that. Let me give, why am I completely convinced of that? Is because this gives me a chance to advertise my student. So she looked at this particular class of spaces, not this, where you take 2 surfaces and you glue them together along embedded essential curves in each one. And their quasi-isometry classes are very different from their commensurability classes. Okay, so these will have pieces like that in them, these mixed Kleinian surface groups. So it's almost surely true that you can be quasi-isometric without being commensurable. But the pieces, the rigid pieces, are rigid. So those pieces, when you're quasi-isometric, will be commensurable. We still don't know. So let me go back to the slide. That's right. She's talking about abstract, infinite many abstract commensurability classes. Yeah, that's right. Okay. So I still don't know. What about a hyperbolic group whose boundary is homeomorphic to the boundary of a mixed Kleinian surface group? For example, just this specific example. Can we find something? So we were trying to prove, so we're in a perfect state of not knowing the answer. We were trying to prove that if you had boundary homeomorphic to this particular example, then you were at least of that type. But now, given the problems we're having trying to understand when you can tell if some collection of curves on a handle body gives you a representation of that handle body as a surface times I, we think that maybe that's a really difficult thing to see. So maybe there's some manifold that looks just like this, but where it's not a product structure, and they actually have homeomorphic boundaries. So we don't know. But this is sort of an important question, I think, at least to me, because we're trying to look at a situation where it has a really canonical surface group in it. It's this surface times I that forms the piece of the hyperbolic piece, but we can't immediately see it from the Bowditch decomposition. So is there some way to detect that either dynamically or with some further structures on the boundary so that we can see it? All right, yes? Yeah, that's right. So
those pieces, can you match up?
Yeah,
something quasi-isometric to that.
If you have something quasi-isometric to that, that's right. It'll have some pieces. It'll have some hanging fixing pieces just because decomposition of the Bowditch, and those will be quasi-isometric. You know, they'll be in one-to-one correspondence with these pieces, not one-to-one correspondence, in correspondence.
So you could sort of find some covers where those bits can be identified in your model and in your mysterious example, and match them up, and there's no way of somehow then arguing that the pieces that are left over match these up.
Yeah, so that's a good point. We're somehow trying to say the pieces that are attaching somehow. So maybe we should restrict to ourselves. I think we're going to have to use these pieces that are attaching somehow. When they attach this way, it makes a product structure. And maybe when they attach this way, like those are going to be important structures for us to understand. So yeah, maybe. Okay, and I will be well behaved and end on time.